So today, we're going to unlock a tool that's used absolutely everywhere, from making your favorite video games look real to navigating financial markets, all the way to quantum physics. We are talking about matrix algebra. And trust me, this is less about scary calculations and way more about a powerful new way to see the world. So let's just dive right in. Think about this for a second. How do you solve a really complex puzzle? I mean, one with a ton of moving parts. Maybe you're trying to figure out the best routes for a whole fleet of delivery trucks, or you're analyzing a biological system where everything affects everything else. How in the world do you keep track of all of that at once? Well, that's where the magic really starts. The answer to handling all that complexity isn't some single, simple number. No, it's an organized grid of them. This beautifully simple structure is called a matrix, and today we're going to pull back the curtain and see exactly how it works. Okay, so let's open up the toolbox. Before we can start building anything cool, we have to get to know the tools themselves, right? First things first, let's meet the matrix. At its absolute core, a matrix is really just a box for numbers, a simple grid. But don't let that fool you. By putting information into these specific rows and columns, we can suddenly perform really powerful operations on huge systems of data all at the same time. It's like organized power. All right, next up is the identity matrix. You can think of this as the number one of the matrix world. Seriously, if you multiply any matrix by the identity, nothing changes. It just stays the same. And that simple, do-nothing job is actually what makes it so important. It's the baseline for everything. And you guessed it, on the total flip side, we've got the zero matrix. It's the zero of the matrix universe. Every single spot in the grid is a zero. It's the ultimate blank slate, the reset button. And finally, for our basic tour, we have the transpose. Now, this is a simple move, but it's incredibly useful. All you do is take the matrix and flip it along its main diagonal. So the first row becomes the first column, the second row becomes the second column, and so on. It's like you're just looking at the exact same information, but from a whole new angle. Okay, so we've met the matrix, but how do we actually do anything with it? Well, you can't just go in and change numbers wherever you want. There are rules. In fact, there are 3 specific legal moves. Think of them as the 3 magic moves that let us solve the puzzle inside the matrix without breaking it. And here they are: swap, scale, and add. That's it. These are the only tools you need. You can swap any 2 rows you want. You can multiply an entire row by some number. Or you can add a piece of one row to another. Just with these 3 moves, we can take any messy matrix and simplify it down to reveal its secrets. So we have our matrix, we have our moves, but what's the point of all this? Well, a lot of the time, we're using a matrix to represent a bunch of equations. And what we really want to know is, does this problem have one solution, no solution, or maybe infinite solutions? The matrix has the answer. The key to this is a really cool concept called rank. Now, for a second, forget how many rows and columns a matrix has. The rank tells you how much unique information is actually packed inside. It's the number of rows that are truly original and can't just be made by mixing and matching the other rows. It's the real size of the information. You know, think of it this way. If you have a row that's just another row, multiplied by 2, it's not really giving you any new information, is it? It's redundant. We'd call that linearly dependent. The rank only counts the rows that bring something new to the table, the ones that are linearly independent. And this all leads to a huge payoff. There's this theorem that gives us a crystal clear recipe. All we have to do is compare the rank of our main matrix of coefficients, let's call it A, with the rank of the whole system put together. And look, if the ranks don't match, boom, no solution. The system just doesn't work. Now, if the ranks do match and they equal the number of variables you're looking for, then congratulations, you've got exactly one unique solution. And finally, if the ranks match, but they're less than the number of variables, the system still works, but you have infinitely many solutions. It's amazing. The structure tells you everything. But matrices are so much more than just equation solvers. A matrix can describe a transformation, like a stretching or a rotating or a shearing of space. And hidden inside every transformation, there are these special unmoving directions, like a true north for the matrix itself. These special directions have a name: eigenvectors. See, when a matrix acts on space, most vectors get pushed around and knocked off their original line, but not the eigenvectors. They stay pointed in the exact same direction. They only get stretched or shrunk. And that stretching factor, that's its eigenvalue.
So how do we find these things? Well, the idea on the left there, that's the concept. It just says applying the matrix to the vector does the same thing as just scaling the vector. And with a little bit of clever algebra, we can rearrange that idea into the equation on the right, which is the one we can actually use to go hunting for those special eigenvalue numbers. And this is where it gets just so cool. These eigenvalues aren't just random. It turns out if you add them all up, you get the exact same number as the matrix's trace, which is just the sum of the numbers on its main diagonal. And if you multiply all the eigenvalues together, you get the matrix's determinant. It's this beautiful, hidden connection that shows you everything is linked. And that brings us to the final and maybe the most mind-bending idea of all. It turns out that every single square matrix has a secret, a hidden equation that it is forced to obey. And it's all connected to those eigenvalues we just met. This right here is called the characteristic equation. I know it looks a little abstract, but this is the magic key. This is the very equation we solve to find the eigenvalues. It's basically asking the question, for what magic number, lambda, does this combination of matrices become, well, uninvertible? The answers to that question unlock everything. And here it is, the grand reveal, the Cayley-Hamilton theorem. And what it says is just profound. It says that if you take that characteristic equation and you replace the lambda with the matrix A itself, the equation still works. The matrix satisfies its own secret equation. It's like a fundamental law of its own being. So who cares? What's the payoff for this crazy secret? Well, it's huge. This theorem gives us unbelievable shortcuts, things that are normally a total nightmare, like finding the inverse of a big matrix, or trying to calculate a matrix raised to the 100th power, things that would take forever. With this secret equation, you can solve them with a few clever steps. It turns brutal calculations into elegant puzzles.
And that's where we'll end it. A matrix isn't just a spreadsheet. It's a lens. It's a way to organize incredible complexity so you can see the simple truths hidden inside. Its true size, its fundamental directions, its own secret laws. And that just makes you wonder, right? What other complex systems are out there, just waiting for us to find the right matrix to understand them?